A very pleasant good evening to all of you who are online. It's very nice to be connected this day. Also, I attend to this session with ease of mind because I don't have to promote data. I have someone who is more interesting who can talk about data engineering in detail. I'm reminded of a quote by Pablo Picasso. He puts it this way: when art critics get together, they discuss about the form, the review, the impression of the artwork. When two artists get together, all they talk about is where to buy cheap turpentine. That is usually what happens with myself and Arun when we get together. I got to know this young man who is an experienced data engineer 10 years ago when he enrolled for a second master's with ISS software engineering track. From then on, we have always traveled together, kept in touch, and shared interesting stories on the landscape. I would like to introduce him as a very professional dragon slayer who has worked on many data projects. He has a wealth of experience, particularly in the data engineering. He has been working on petabyte projects, consulted for various clients in different portfolio, and he always shares the best practices session. So let us listen from him what he has to share as ideal way of handling large data structures, in particular, probabilistic data structures. And I hope by the end of the session, the practitioners who are watching will have some takeaways. And if you are an alumni, you're watching, and you would like to share such interesting case studies and stories from your experience, please write to me and write to the team. We'll see how to introduce your wealth of experience to the public participants as well. With that introduction, let me give the stage to my student Arun, and a warm welcome. I hope you enjoy this session. Thank you.
Thank you, ma'am. That was really helpful. Thank you. All right. Okay. All right. For the next 30 to 40 minutes, we'll be talking about a really clickbaity title called Approximate Now is Better Than Accurate Later. It's an introductory talk into how we can use some of the probabilistic data structures in big data. So why are we, in specific, what we're going to talk about is two probabilistic data structures. We'll take two problems, and then we'll talk about that in detail. But before that, why are we actually talking about probabilistic data structures? Why do we even care about it? The reason is pretty simple. It's because the data in which we are now storing is growing at an incredibly faster pace. We are now the amount of data that we're dealing with on a day-to-day basis is massively larger than what we used to deal with a few years ago. So just to give a perspective of where we are right now, we have about 500 million tweets per day, and that's quite a lot. And we have about 3.5 billion Google searches per day. And just to take it out on home, if you think that the rest of the Google or Twitter is actually one of the very few companies which deal with that kind of a scale, and these are outliers, that's not entirely true. Our own Singaporean company Grab has about 50 million writes per day. And in a mid-sized company, bank which I used to work with, we used to deal with 3.3+ petabytes of data. And these are the data that we are expected to analyze on a day-to-day basis. So that's all good. We have quite a lot of data, but what's the deal? What's a big deal about having so much data? We have variety of spectrum of things in which we can look at data. They call it the 3 Vs and 4 Vs and now 42 Vs and so on. But we'll specifically take two aspects of big data. One is volume, another one is velocity. Volume, like we just discussed about, it deals with, we have a lot of data. So what it means is that if you're talking about data in terms of petabytes, we surely know that all of the data cannot be stored on a single machine. So this has to be distributed across multiple machines. The moment we distribute data across multiple machines, we know that simple problems such as counting is really, really hard. So say, for example, if you have data stored across multiple machines, and if you wanted to just do a simple count of all the rows which is distributed across many machines, the easiest way that we could do about is that we have to collect the data, we have to run distributed processes, and we have to collect data from every single machine and then consolidate them together before coming up with the final output. That's one aspect of it. The other aspect of it is the velocity. See, the speed in which we get the data. The amount of data is one aspect of it, but the speed in which we get the data is also another interesting aspect of it. So we have wearables, we have social media, even washing machine talks these days. So we are collecting a whole lot of data, and it comes at incredible speed. And this is going to keep on increasing the moment we see 5G coming into play, the amount of data that we are getting at a real time. So now we'll take, but the other aspect of it is that while we're getting data in real time, we are hungry for insights immediately as well. As and when the data comes in, we are really, we wanted the insights out of it immediately. But the good news is that we are not actually keen about getting the accurate information. Say, let's take this example of top 10 Twitter trends, right? We have the trending topics. And if you can see the numbers, say we have about 355,000 tweets on TikTok ban alone. This was, I think, last week. So, but if you think about it, do we really care whether the number 355,000 is actually 355,000 or it's 355,459? We don't care about the accurate number. We are in the business of looking at approximations. But is it okay for us to get this exact number, so 355,459 tweets at the end of the day, or are we interested in looking at the numbers in real time? We are actually looking at we wanted the information in real time as well. So that's the other aspect of it. While we have a lot of data, we have the data coming in a really faster pace, we wanted the information or insights out of this data on a real-time basis. That's one thing. So if you wanted real time, then it comes at a cost, right? Because nothing is free in software, so it comes at a cost. And we are going to, while we are getting data and insights in real time, we are going to pay it in some other means in terms of memory or CPU or disk space. That's the other aspect of it. So in this talk, in about next 30 minutes, what we'll be talking about is we'll take just two problems. One is related to volume, another one is related to velocity. We'll take these two problems. One of the problems is related to volume is called membership, and the problem that is related to velocity is frequency. So we're going to take these two problems, dissect them into pieces. We'll look at how we traditionally solve this problem. At the end of it, how can we actually go about using a probabilistic data structure in order to solve this problem as well. So what does membership mean? Does the data set contain a particular element? Okay, that's interesting. And what does frequency mean? Who are the heavy hitters, or what are the top K elements? Okay, that's a mouthful. Let's look at the same problem with an example, right? Say membership. Say assume that you're working for Google and you're in the Gmail team. Okay, so you have a bunch of you know that you're following the news, and then you see that every day millions and millions of passwords are compromised and it's leaked on the internet. Now, you as a Gmail engineer who is belonging to the Gmail team comes up with an idea saying that you don't want any of your users to select a password which has already been compromised in public. So you have this bunch of compromised password which you can easily find on the internet by a simple Google search, and you don't want the users to actually select any of this password. This is a good problem. This is actually a good problem to solve. That's one thing. So the other bit of problem is that, say, assume that you have a large file which spans to, say, a few terabytes of data. And then you wanted to large documents, so you have a few terabytes of file, which is one single document. And you wanted to make sure, you wanted to check whether the string that you have, say, for example, if you're searching for, say, NUS, you wanted to check whether the presence of this particular word is in that huge document. So this is also membership. So what membership actually means is that you have a large data set, and you're just going to check whether the element that you're going to that you have is in that data set. That's all you're trying to do. That's it. The second bit of problem that we will be looking at in detail is frequency. Frequency is something which we can actually closely relate to. These are, say, for example, in Twitter, we looked at what are the top trending topics. What are the top most sold items in Amazon? Or what are the most watched YouTube videos this week? Or the TikTok views or Instagram likes. I mean, you wanted to see which is the most popular one as well. That's the frequency. These are otherwise known as heavy hitters. Okay? There are a few other problems which we could solve with probabilistic data structure, which we're not going to go into in detail, which are some example like cardinality or quantiles or similarity. Okay? All right, the way that we are going to look at this problem, the membership or the frequency, both the problems, is that this is a structure that we're going to follow. We're going to take this problem. We're going to say, in this example, in terms of Gmail, we took the problem. We'll dissect the problem in detail. And then we'll do a back of the envelope calculation if we are to solve this problem using traditional means. And then we'll introduce a probabilistic data structure. And then because you don't want to believe why a probabilistic data structure would work, we'll also go into how these probabilistic data structure internally works as well. So without understanding a data structure, it doesn't make sense for us to use it in the first place. So that is the reason we have this fourth item as well. Okay. All right, let's take membership. So membership is, does the data set contain a particular element? That's a gist of the problem itself. See, we'll elaborate on the same example that we quoted earlier. So we have your Google engineer, and then you wanted to make sure that the user in Gmail does not select a compromised password. This is good. So you look up the internet, and you saw 1.4 billion password breach compilation word list. You have a huge password list, 1.4 billion passwords, and you wanted to make sure that the users does not select a password which is in this list. That's the gist of it. So you do some back of the envelope calculation. You see 1 billion passwords. So let's say 1 billion passwords, and each password is about 10 characters, which is 10 bytes. And then we do a simple math, and then we can see that 10 GB on disk is being used. And if you wanted to just keep it in memory, it's about 64 gigabyte in Java itself. The other languages could differ a little more, but 64 gigabyte in Java. So how do we solve this problem in traditional way? We can use a database. We can just dump the entire password list into a single column in a database. And then every time a user selects a password, you just go and check in your database whether this password is available in this particular data set. It's as simple as that. It's very low cost. It's 10 GB on disk is not much because disk is considered really, really cheap. But at the same time, in terms of scale, in Google scale, we're talking about hundreds and thousands of requests per second. And it does not scale as much as we like it to be. And these checks are expected to be really low latency as well. And if you look at the latency numbers itself, we can see that looking up the disk is 100,000 times slower than looking up in memory. Okay, so you decide that, okay, let me solve using memory. Okay, so you can actually solve this using memory itself. So what you can do is that you can actually take this 1.4 billion password list and put it into a hash set in memory. And then when a user selects a password, you can check whether this particular password is in the hash set itself. So that, what does it come to? It comes to about 64 gigabyte in memory. That's quite a lot. And for a single machine to have 64 gigabyte, you're spending quite a lot of money on that as well. It's faster, but at the cost of some more money. It's not only that, right? Because while you're talking about database and memory, we are completely ignoring the fact that it must be highly available as well. So you cannot have this entire service on a single machine. So you have to have this particular service spread across multiple machines. So obviously you're going to replicate it, or in the best scenario, you're going to slice the data, which is shard the data, and then spread it across multiple machines. So you not only have high availability, but also high scalability. So typically your 10 GB or 64 GB is not just 10 GB or 64 GB, but it has to be multiplied by the number of replicas and shards that you actually have. And then the moment you have this data spread across multiple machines, the way that you can actually consolidate all this data into, say, just to have a password, just to check the password, whether the password is actually present in the entire list, you have to query up multiple machines in order to come up with the final result, right? That's one thing. All right, okay. So why the whole build up to this one is primarily because we have a solution to this. Just that we can actually solve this problem. Instead of using 64 gigabyte of memory, we can actually solve this problem using just 1 gigabyte of memory, provided you're willing to let go of 1% accuracy. So what does 1% accuracy actually mean? Is that, let's take this example of Gmail, right? The user has selected a password. Say, some of the times the user might have actually selected a secure password, but we would actually tell the user saying that, no, you chose a compromised password. That's the 1%. 1% of the time, even if the user selects a secure password, we might end up saying that it's a compromised password. That's the accuracy bit. Say in terms of a huge file, so we might sometimes say that this particular data that the user is actually looking up is actually present in the file, while it was not. In which case, what is the downside that could happen? Then the person who is looking up, who wants to search in this file, has to go through the full file scan anyway. So it's not actually that bad. The 99% accuracy is not actually bad. While I'm saying this 99% accuracy, it need not be 99%. It could be 99.99 or 99.999. It's a give and take that you're actually playing with. So the way that we can solve this problem using 99% accuracy, the data structure that we can use is what is called as a BloomFilter. BloomFilter is a space-efficient probabilistic data structure that is used to test whether an element is a member of a set. That's the what do you call, theoretical definition for that. What does it actually mean? It just means that you have a bunch of you have a big data set, and then you have one element, and you're gonna check whether this element is actually present in that data set. That's what it means. And it's space efficient, and it is probabilistic data structure as well. That's all it means. The second property of the BloomFilter is that false positives are possible, but false negatives are not. So what does it actually mean? It's the same thing that we discussed just now. So the password the user would have chosen might be secure, while there is a case wherein we might end up saying that the password is actually not secure. That's the false positive. The other bit is that false negatives are not possible. What does it actually mean? It means that there will never be a case wherein the user has actually chosen a compromised password, and we ended up saying that it's not actually compromised. There is no chance of doing that. That is the most important property of BloomFilter itself, and which is very closely tied to what we actually want in the first place. All right, so now we are hooked up. So we wanted to know how BloomFilter actually works, right? So the internals of BloomFilter is actually very simple as well. It's very intuitive, and it's very easy to reason with. So it just has 2 steps. And it's very obvious as well, the moment you see it at the end of it. So assume that you have this the 1.4 billion passwords, right? And the way that you construct the BloomFilter is that as a first step, you run this passwords in the password list through a bunch of hash functions. When I say bunch, it generally ranges between 3 to say 9, or it's generally in a single digit number. So in this case, I've chosen 3 hash functions. And then say I take the first compromised password, which is password 123. I run it against hash functions, and hash functions typically give us a hash code, right? Which is, in this case, it gave 5, 2, and 7. I ran it by 3 hash functions. One is MD5, murmur3, and FNV1. So this is the first step. So we just take the password, we run it against a bunch of hash functions. The second step that we're going to do is that we're going to populate this. Populate a bit array. Bit array or bit set is nothing but an array of bits. That's it. It's either a true or a false, or a 1 or a 0. That's it. So the result of the hash function, we got 5, 2, and 7. What we are actually going to do is that take the index 5, take the index 2, and take the index 7, and then set the bits of the array to be 1. That's it. We're just setting the bits. So we in a huge array, we have say 8 elements in this array, and we're just setting the bits 2, 5, and 7 to true. That's it. So that is all the BloomFilter is all about. Now let's take another example wherein we have guessed 1 to 3, as a new password, the second password in the 1.4 billion password list. So what we're going to do now is that we're going to run the guess123 through the same list of hash functions. So MD5, murmur3, and FNV1. In this case, we got 3, 2, and 1 as a resulting hash codes. So what we're going to do is that we're going to take, in the array, we're going to take index number 3, 2, and 1, and we're going to set the bits of 3, 2, and 1. And if you go back a little, I'm just going back a little. So if you can see, when we hashed password 1 to 3, 5, 2, and 7, 2 has already been set. And in guess 1 to 3, 1, 2, 2 is again being set. So it doesn't matter. I mean, there is going to be collisions. So if you're running the passwords against a bunch of hash functions, there is going to be collisions, in which case it's totally fine. And that is the reason why BloomFilter has this property of having false positives. Okay. So now, so you have this whole BloomFilter. Assume that you have already populated 1.4 billion passwords. And then now the user selects guess 1 to 3 as a password. And now you wanted to check inside the BloomFilter whether this password is actually present or not. So the user actually got guess 1 to 3. We're you're running it against the hash functions 3, 2, 1, 1, and you're going to check whether the existing BloomFilter has these bits set. In this case, it is set. So we're going to tell the user that, you know what, this particular password that you chose is actually compromised. That's it. That's the end of the story. Now, I did say that there could be a case wherein the user selects a secure password, but we ended up saying that it's actually, compromised. This is a scenario for that. Say, assume that the user has selected secure @ percentage and $. So this is a secure password. And then now what we are going to do is that, the process is very similar. So we are going to run this password against a set of hash functions that we have already selected, MD5, murmur3, and FNV1. And we got the hash code as 1, 3, and 5. Now, because the array already has set 1, 3, and 5, the index is 1, 3, and 5, as a result of hashing password 1 to 3 and guess 1 to 3, we are going to tell them that the password has been compromised because we are not sure what is the original password in the first place. So at the end of it, we are going to tell the user that it is a compromised password. So this is where the false positives come into play. Now, this is not good, right? Because we wanted the false positives to be as minimal as possible. So how do we actually go about reducing the false positives? The way that we will reduce a false positive is by 2 means. One is that the array size can be really large. It need not be 8 in our case. We just had an 8 element array, 8 size array. But instead of that, we can actually have the array to be a few million, or say we can. It depends on how much elements are you actually inserting into this BloomFilter in the first place. And there is a very simple formula just to plug it in and then figure out what is the size of the array elements as well as a number of hash functions. So we can reduce false positives, and it's easy to just reduce a false positive to a really small number, provided you're willing to have an array which is larger or have an extra bunch of hash functions. In this case, we have about 5 hash functions, and then we have the array size is about 8 billion, and this comes about less than a gigabyte. And we have a false positive percentage in this case of about 0.2%. All right, so where is actually BloomFilter being used? It's being used in many, many different NoSQL databases. I mean, the modern NoSQL databases, pretty much most of the popular ones use BloomFilter as a first level of check whether the data is actually present in that entire database. Instead of going through the petabyte scale database and trying to find the exact data element, instead of that, we can actually have one level of checks beforehand wherein we are checking whether the data is actually present or not. Because BloomFilter has a property of having no false negatives, if the data element is actually not present, BloomFilter will immediately say it's not present in the first place. That's a good news. Say YouTube and Medium actually uses BloomFilter in order to not recommend videos which you have already seen. Or read articles which you have already seen. Yeah, so that's a very good feature, and you can easily build it in your own application itself. All right. The second data structure or problem that we're going to see is what we call as a frequency. Who are the heavy hitters or top K elements in your application? So this is much more closely related to what we can relate to easily. So in terms of graph, we have about 50 million writes per day. We wanted to analyze what are the top trips this month. So what is the from to combination of trips this month, which is easier for graph to analyze and then position drivers in such a way that they have more traffic coming into their app. So in terms of YouTube, we have about 5 billion YouTube videos watched per day, but we wanted to see what is the most watched videos today. In terms of Twitter, we have about 500 million tweets per day, but Twitter is able to keep track of what are the top trending topics this week or this month or this year. These are good problems, and we can easily relate to these kind of problems. So let's. The good news is that, like I mentioned earlier, the good news is that we are not actually looking for accurate numbers. And the moment you see accurate numbers on internet, you can be rest assured that it's a lie. Because in real time, if you're dealing with large amounts of data, and if you wanted statistics in real time, it's almost always true that the statistics is not accurate, because there has to be some compromise somewhere. I mean, it's nothing is for free. And you can look at in Twitter's documentation somewhere, it would say that the number of trending topics, the number of tweets that you see in the trending topics, it's actually an approximate number, which is true for all the other cases as well. So let's pick up a problem. In this case, we'll pick up Grab. Say Grab has about 50 million writes per day, and a problem that we're going to solve is that we wanted to analyze what are the top trips that happen this month. So let's do a back of the envelope calculation. We have 50 million writes per day. It comes to about 1,500 million writes per month. Let's take a ballpark estimate of 10% of them are unique writes, and then we have about 150 million unique writes per month. And 150 million writes per month, if you wanted to put it in, say, key value store as a write, the trip itself, the source destination combination, the trip itself being the key, and the counter, the number of trips is made as a counter, which is 4 bytes in integer, which can handle about 4 billion numbers. So what we can do is that if you take about 150 million unique writes and 4 billion 4-byte counters, you can easily see that the total amount of data structure in memory comes to about 10.2 gigabyte in memory. That's quite a lot. I mean, just to have this per month. And if we're just talking about per month statistics, what if we wanted per day statistics or per year statistics? So we can't keep all this information in memory at the same time, but we can. So using this data structure called count-min-sketch. Count-min-sketch, again, the definition of count-min-sketch is count-min-sketch is a memory-efficient probabilistic data structure that allows one to estimate frequency-related properties of data. What it simply means is that we can use this data structure to count. That's all it means. And the way that, what are we actually trying to solve using this count-min-sketch data structure is we are trying to find the top K frequent elements or heavy hitters in our application. So if we use count-min-sketch, what are we actually gaining? For 150 million keys and counters, the way that we saw was which took about 10.2 GB of memory. With 99% accuracy using count-min-sketch, we just need to use 82 MB of memory. That's quite a significant improvement from what we used to be. 82 MB is not a lot at all in modern terms. So how does it actually work? How do we construct a count-min-sketch? It's very, very similar. The structure of count-min-sketch is very, very similar to BloomFilter itself. And the process of constructing count-min-sketch is also very similar to BloomFilter. In terms of BloomFilter, what we actually did was that we ran this input string, and then we ran it against a bunch of hash functions. And then we populated an array, a bit set array, and we set whether it's a true or a false. In terms of count-min-sketch, what we actually have is that every single hash function actually has its own array. And one other thing which you can obviously notice is that it's not a bit array anymore. It's actually an integer array. So we can actually increase the numbers, now the values within the array itself. All right. So there are just two steps again, just like for count and sketch. One is hashing the input. Say, for example, we have this City Hall to Bedok. This is a trip, and we just combine them together as one key. So City Bedok. And then what we are going to do now is that just like BloomFilter, we are going to run the City Bedok string against a bunch of hash functions. In this case, I've chosen 2 hash functions, k equal to 2. And I've ran it against a bunch of hash functions. And then I got the result as 5 and 3. Just like BloomFilter, I'm going to go into that corresponding 5th index and the 3rd index. And I'm going to increment the value by 1. So it was the earlier value of 5th index used to be 5. Now it's 6. And then earlier value of, say, 3rd index used to be 1. Now it's 2. Say, assume we have another trip now. We have City Hall Bedok again. And then we saw that earlier it was 6. Now we are running against the same bunch of hash functions, and now it's become 7 and 3. So literally what we are trying to do is that we are based on the trips, and now we are just incrementing the array integer values by 1. That's all we're doing. Let's take another example, right? So we have, say, how do we now that we have actually have City Hall and Bedok, we have 7 and 3 as its own frequency. Now we wanted to estimate the frequency itself. So in order to estimate the number of trips for City Hall to Bedok, what we're going to do is that we're going to run it against the same bunch of hash functions, MD5 and MAMA3. And then we got the index 5 and 3. And then in order to estimate the frequency, we go to the corresponding index values, which is 7 and 3. And then we're going to return the minimum of the 2. Why are we returning the minimum of the 2? Because remember in BloomFilter we had this collusion. The value 7 could have been incremented. The value in index 5 could have been incremented by some other trip altogether. So we wanted to make sure that we are conservative about making our estimate. That's where the approximation come into play. So in this case, we took City Hall and Bedok, and then the result of the hash function is 5 and 3. And then the value of the estimation is actually 7 and 3. And we took the minimum, which is 3 in our case. And then, but that is not the problem that we are trying to solve, right? In Count and Sketch, what we actually originally intended to solve was we wanted to find the top k elements. In this case, top 3 or top 10 or top 100 elements. Let's take this case of top 3 elements. So we wanted to find the top 3 trips in Grab this month. So the way that we will maintain the top 3 elements is by using a data structure called heap. It's a min heap. So what it means is that we actually, if you're not familiar with the data structure called heap, what we can assume is that it's like a sorted array. We can just keep it like an array, so which is of fixed size, which is 3 in this case. So the way that we maintain the top k elements is that we initially maintain a heap, which is of fixed size. And the next step that we do is that, say, assume that a new trip comes in. In this case, a new trip is called Clementi Harbor. So which is from Clementi, the person is moving to Harborfront. So this is a key for them. So the way that we would maintain this top k element heap is that every time there is a new insertion or a new insertion into this array, which we call as a frequency array, the moment we insert or increment the value inside the frequency array, then we estimate the count of that frequency array as well, of that particular trip itself. In this case, we have Clementi Harbor. We ran it by MD5 and MAMA3. We incremented the value in index 7 and 8. And then the estimated count of Clementi Harbor is now 3. And then now we take the number 3 and we compare this value against the minimum value in the top k elements. And we can see in the top k elements, the minimum value is actually issued to airport, which is number 2, which is a total count of 2. So now we see that the estimated count that we have for Clementi Harbor is actually greater than the minimum value in the heap. So what do we do about it? We just throw away Yishun to airport, and then we replace with Clementi Harborfront. That's pretty much it. So at the end of it, our top k elements array will always have only the top 3 elements in in the entire list itself. So now if you wanted to just get the top k elements, we just need to return this entire heap, the top k heap. That's pretty much what I have. So what we actually saw was that we saw two probabilistic data structures. One is used for membership, another one is for frequency. For membership, we saw BloomFilter as the data structure. Like I said, membership is a problem wherein we have a large data set, and we are trying to check whether the new element that we have is actually part of this bigger data set. That's the membership problem that we have. The second data structure, probabilistic data structure that we saw was count-min-sketch. Count-min-sketch is actually used for estimating the frequency, and by way of estimating the frequency, we can also maintain the top k elements in your application or whatever use case that you have. We have many other probabilistic data structure. In the interest of time, we just discussed two of them. We have HyperLogLog. We have a variety of variants to the BloomFilter itself. We have a way to measure quantiles in real time. And you can see that many big data frameworks, say Spark or Flink or Beam or whatever you can use, actually uses one of these data structures to actually give input to you, give metrics to you in real time. And those metrics are, you have to now understand, they are not accurate metrics, they are actually approximate metrics. One thing which I wanted to call out at the end of it is that while we are talking about, say, for example, Twitter's frequency or YouTube video numbers, right? So we are actually saying that these numbers are approximate numbers, but that is not entirely true as well. Generally, what happens is that while we're using these probabilistic data structures to have approximate estimations in real time, there is generally a case wherein people run end-of-the-day jobs at the end of the day, wherein they accumulate the real data, the accurate information, and then at the end of the day, they sync it with the actual information. So during the day, it's all approximate information. At the end of the day, they replace approximate information with accurate information. Because we can't afford to run these end-of-the-day jobs real time because they are inherently slow. And that is the reason we are using these approximate data structures. So the key takeaway that we wanted to take away from this one is that we have a whole lot of probabilistic data structures that we can use. And if your use case is actually large volume, and then you wanted real-time analytics, probabilistic data structure is a go-to place wherein you can actually gain all this goodness of real-time information or real-time insights, while saving a whole lot on performance, on space and memory and CPU, other costs itself. That's all I have. Thank you.
Thank you.
Thank you.
That was a very insightful talk, and that kept me wondering about the many situations where you can apply probabilistic data structure. So those who are out there listening to this online talk and are interested in coming in and joining the data cert or any of the master's graduate certificate program, you're welcome. So we have a whole suite of courses that are related to big data, data engineering, information design, and insights engineering out of all this new generation oil, which is data. So to be very specific, we start off with the data modeling course, which deals with all different types of polyglot persistence, the different kind of data structures, the scalability aspects of them, and of course, to be very specifically, information architecture design for insights engineering. Then we have a foundational course, which sometimes Arun comes back to help us on industry case studies and practitioners' perspective as well. So this is an entire technical stack that discusses big data engineering, very specific to analytics, where we have a lot of use cases which are very specific to analytics. We discuss the Spark technical stack, which has got various aspects of special libraries. We have machine learning discussions. We have graph analytics discussions. We have real-time streaming discussions, which Arun was talking about. And that is why this kind of probabilistic data structures as well. So we also have a lot of fun tech stuff like Spark, Flink, Splunk, few of it which you heard him mention. So thank you very much. And There's also two tracks inside this data set, one specializing on the software track and the other one specializing on the business analytics part of it. So feel free to look at the website to understand more details. There's also a QR code being displayed on the talk window. So feel free to put us some feedback so that we can take pointers to see how to align ourselves better regarding this talk, as well as the kind of the way that the things have been arranged. Thank you very much. So there are a couple of questions. So I will let, I'll let Arun take up the one on MD5 first, if you're prepared.
All right. Okay. So the question is, why does MD5 return a single digit when usually it returns a long string? I mean, I just simplified for the sake of the presentation itself. MD5 returns a long hexadecimal string. Just that at the end of any hashing function, if you wanted to bucket the resulting hash into some form of bucket, we generally do a modulus on the size of the array itself, right? I just removed that from the part of the presentation itself. Yes, MD5 returns a long string, and then we can actually convert that to a number, and then we can do a modulus on top of the on the resulting number to fit in order to fit into the array itself. Yeah.
On a lighter note, we use that kind of calculations for take-home assignments.
The second question, you want to take it now?
Oh, yes. So there is a question that asks about the link that I was talking about to the certificate. You can find them on the official ISS website. Okay? So we have pointers to all the 4 different master's program that is being offered as graduate cert. Each of them is composed of general certificate as well as specialist. So please feel free to link it up through the website. Thank you very much. There is also another question that Arun wants me to answer, though it is pointed to Arun. And this is funny. We are very good at arrowing each other. So this is what we talk about initially as the turpentine talk. So the question asks about, if I'm a beginner in data science, seems like a lot of technical knowledge that is needed to work in big data. Where do you recommend to get started? That's a very interesting question. I don't know what Arun feels about it. 10 years ago, when he came into my class, I first introduced the Hadoop stack. I had no clue what I was learning, and I never thought MapReduce framework is going to influence the world this way that it has done. Okay? So not just to the participant who has put this question, but to any big data engineering beginners, this is my very simple piece of advice. Advice is not a good word, suggestive quote. Okay? So if you're looking at building an experience or a knowledge set in this area, the best way to go about it is to start doing things by hand. And of course, when you want to build things by hand, there's a lot of jigsaw puzzle Lego system that you have to go through. So there's a knowledge piece, there's a skill piece. There's a knowledge piece, there's a skills piece. Always try to scope down. A very good example was what Arun was trying to approach today. So there are so many problems. See, the velocity, volume, all these things are metrics. There are like a dozen metrics that are around there in big data, but he very clearly scoped out one example each and only took 2 of these metrics. One is the velocity and the volume, because those are the very niche metrics that people are interested on real-time systems. So very similarly, you scope out what you want to pick and then try building small models. In my humble opinion, however accurate, however fantastic your model is, the best accuracy comes from the inclusiveness of the big data. So one of the foundational things that you got to pick up is to see how you can tap on these various data resources to build fruitful projects. So start small, do multiple pieces of projects and showcase them. There are multiple ways to show digital presence these days. These things should get you started to cruise through this ocean. Was it right? What is your comment?
That's pretty much it. You're right. So yeah, I don't have anything to add. But to ma'am's point, I think getting started somewhere is much better than not starting at all. So that's a good point. So so in terms of big data itself, it's a whole big space. And then so if you're coming from data science background, we just can you can start from, say, if you're already building models on a single machine, the next big step or a good step to start is to actually use a distributed framework in order to do the same thing that you're comfortable with. And then the moment you actually scale up your machine learning model in order to be trained against a large distributed framework like Spark or Flink or whatever distributed framework actually which offers machine learning model training, then you would obviously be exposed to a whole lot of distributed computing problems. And then that's a good place for you to start. I think scavenging is one of the good ways of actually learning, in my
Though
opinion.
I don't agree with the word. Yeah. That's not sounding very pleasant. Yeah.
I'm sorry about that.
Just kidding. Yes. So that was a very good comment. So that's a very good place. So start small, try projects, very particularly as Arun has hinted, look for distributed platforms. Okay? You can be a Python expert. You can be an R guru, unless you're going to challenge yourself by scaling into multiple sources, which are very large. You're not getting the skill of distribution. So scalability is the key essence of big data projects. Please see if you have some tech stacks that support that. That would be the best place to start big data projects. So yeah, thank you very much.
Thanks a lot.
Thank you very much.